Welcome to this session. Today we are going to discuss some more problems on groups. In the last class, we discussed group and its properties and some of the problems. Now the continuation of the previous session, we are going to solve some more problems which are related to groups. Now, the first problem is show that the set of all positive integers from an abelian group under the composition defined by A star B is equals to AB by 2. So here the binary operation is given as like this, AB by 2. We have to prove that which is an abelian group, under the composition. Now, see here where the set is a positive rational numbers. Here the given set as positive rational numbers. So we are taking it as Q plus denotes a positive rational number. And of course, star is the binary operation, and if it is defined like this, and we have to verify whether it is a group or not. If it is a group, then we have to verify whether it is an abelian group or not. So here, set of positive rational numbers. So here, if I am taking two elements as a rational numbers, then the product is also a rational number. So A, B are any two rational numbers. If I am taking A, B belongs to Q plus positive rational numbers, then AB is also a rational number. Then AB by 2 is also a rational number. So which is obviously a positive rational number. So which is obviously belongs to Q plus. So I can say that star is closed. Next, another one is associative property. So here, let us consider the three elements. A, B, C belongs to Q plus. A, B, C belongs to Q plus. Whenever if they belongs to Q plus, now we have to verify the associativeness. We are going to verify the associativeness. For that, we are going to prove this. A star, B star, C is equals to A star, B star, C. So we have to verify this. So this is by definition, by defined A star B is A by 2. So similarly, B star C is nothing but BC by 2. And here this is nothing but AB by 2 and star C. Or else A star B, once again the same operation, A star B, which is nothing but A, BC by 2 by 2. So similarly, AB by 2 into C. So this is A, B, C by 4. Then this is A by 2 will be there by 2. So A, B, C by 4. So obviously both are same. So we can say that it satisfies associativeness. And now the identity element. So which is going to be identity element here? So here let us consider if I am taking an element. First of all, we are going to find what is the identity element. Whether that identity element is a member in that or not. So what is the identity element? Suppose E is said to be an identity element if A belongs to Z, then A star E is equals to E star A is equals to A we have to get. Suppose here I am just considering, then I have to take it as, okay, so this is the identity element. Let us say, I am just saying that if B is the identity element, then A star B is equals to B star A is equals to A. is equals to A. So now what I am saying that, so A star B is equals to then AB by 2, or else I am just taking this is any one. If I am taking AE by 2 is equals to A. I am just taking this one and this one. I am not considering this. These two I am taking. So AE by 2. So what is AE is 2A. So what about A get cancelled. So E is equals to 2. If I am taking these two, otherwise these two also if I am taking, E star A is equals to A. So EA by 2 is equals to A. So EA is equals to 2A. So these two. So E is equals to 2. So what is the identity element? If I am taking E is the identity element, then E must be equal to 2. E must be equal to 2. 2 is also belongs to Q plus. 2 belongs to Q plus. So it is having the identity element. It is having the identity element. Now we have to find out what is the inverse of each and every element, whether it is exist or not. Whether it is exist or not. So that we have to find out. Let us consider generalized. If I am going to take A is the B is the A is an element in Q plus, and I am just taking B is the inverse of A. B is the inverse of A. Then what I am going to get? B star A star B or B star A is equals to the identity element. What I am taking? I am going to verify whether B is a member in Q plus or not. Whether B is a member in Q plus or not. So what is this? AB by 2 is equals to E means identity element, it is 2. Identity element, it is 2. So what is B is equals to? B is equals to 4 by A. B is equals to 4 by A. So A inverse is equals to 4 by A. What I am assuming that I am just taking A inverse as B. A inverse as B. So in such a case, A star B is equals to B star A is equals to the identity element. The identity element. So here, if I am taking B star A is equals to identity element, what is that identity element? Is 2 here. So then it is a BA by 2. BA by 2 is 2. So B I have to calculate. So it is 4 by A. So here 4 by A, here 4 by A. I am saying that whether 4 by A is a member in Q plus or not, it is nothing but a rational number. It is nothing but a positive rational number because A is positive. Because A is positive. Subsequently, 4 by A is also, 4 is a positive. So 4 by is also a positive. So which is belongs to Q plus. Which is belongs to Q plus. So each and every element will have a inverse in Q plus under the binary operation as composition. So we can say that this Q plus comma star is a group. And now we have to verify whether it is an abelian group or not. So now we have to prove that AB is equal to BA. AB is equal to AB by 2. A is a positive rational number and B is also a positive rational number. So product of two rational numbers can be written as BA. AB is equal to BA. So I am going to convert it as a BA and by 2. So this is nothing but a B star A. So it is going to be satisfies the commutative law. So we can say that this is an abelian group. This is an abelian group. Now let us go for the other example. So one set is given. Show that the set G is equals to 1, 2, 3, 4, 5 is not group. Under addition and multiplication modulo 6. Under addition, multiplication modulo 6. So here, additive modulo 6. First we are going to verify additive modulo 6. After that we are going to multiply the multiplication modulo 6. So first of all, what is a modulo 6 operation? What is a modulo 6 operation? So here, A plus B under modulo 6, if I am going to add these two, if the resultant is greater than this, then this number is going to be subtracted. Or else I am going to write it as A into B, or else A is congruent to B modulo N if I am taking A minus B is divisible by N, or else I am just taking in another way as just adding these two numbers. If it is greater than that, I am going to write that as a factor. This can be written as 1 into 6 plus the remainder we are going to get. That means 7 minus 1. 7 minus 1 is divisible by 6. Like that we can express. Now just I am going to take just addition. I am going to take and I can write that as a factors of this. Okay. Now 2, 5 under additive modulo 6. I am selecting two elements. 2, 5 belongs to G. I am selecting two elements. I am going to verify additive modulo 6. So 2 plus 5. 2 plus 5. Of course, additive modulo 6. So this is equals to 7. This is equals to 7. 7 is greater than 6. So I can write this as 6 into 1 plus 1. 6 into 1 plus 1. So next that means here I am just taking, and another one is 3 plus 7, 3 plus 5. Let us take 3 plus 5, which is 8. 8 I am going to write 6 into 1 plus 2. 6 into 1 plus 2. Suppose if I am going to consider 4, 5, 4 plus 5, I am going to take it as a 9. So 9 can be written as 6 into 1 plus 3. Plus 3. So like that, if it is exceeds 6, I am going to write. Otherwise, I can write same as these numbers. Same, I am going to write the same number. See here, 1 plus 1. So it is a 2 I am going to get. So 2 is a lesser number, lesser than 6. So I am just taking 2 alone. Next, 1 plus 2, it is 3. 3 is lesser. 1 plus 3, 4. 4 is also less. 1 plus 4, 5. 5 is also less. 1 plus 5, I am going to get 6. I am going to get 6. So I am going to write 6 as, then if I am going to divide 6 by 6, 6 minus 6, the addition is, I am going to get 0. So I am going to take it as 0. Just subtract from that. 7 minus 6, 7 minus 6, whatever the values will be there, those values I am going to write. So 6 I am going to get here, 6 minus 6, so that value will be 0. Here, these values I am going to write. So here I am going to write, how I am going to write, see 1 plus 5, 1 plus 5. So I am going to write it as 6, and 6 can be written as 6 into 1 plus 0. 6 into 1 plus 0. So that the 0 I can write. Or else, if it is exceeds directly, subtract 6 from that. If it is lesser, directly write those numbers. So that is also right. Now 2 plus 1 is 3, 2 plus 2 is 4, 2 plus 3 is 5, and 2 plus 4 is 6. 6 is, again I am taking 0, and 2 plus 5 is 7. 7 I am going to write 1. 7 I am going to write 1. Next 3 plus 1 is 4. 3 plus 2 is 5. 5 is lesser than 6. So I am taking same number. 3 plus 3 is 6. 6 is, so I am going to equal. So I am going to write this 0. And 3 plus 4, it is 7. 7 I am going to write 1. And next 3 plus 5 is 8. 8 I am taking 3. And similarly like that we are going to follow. 5 plus 1 is 6, so 0. 5 plus 2 is 7. 7 I am going to write it as 7. 5 plus 2 is 7. So 5 plus 2 7. 7 I am going to write it as 1. And 5 plus 3 is 8. 8 I am going to write it as 2. And 5 plus 4 9. 9 it is 3. 5 plus 5 is 5. 5 minus 5 plus 5 is 10. So 10 minus 6 it is 4. It is a 4. Now like this I am going to fill the table. I am going to fill the table by using these operations. By using these operations. Now we have to verify. We have to verify whatever the elements here, whatever the elements that were mentioned in the table, all elements are members in G or not. If all elements are members in G, obviously we can say that it is closed. It is closed under additive modulo 6. Otherwise it is not closed. Otherwise it is not closed. See here, I'm going to get 0, 0, 0, 0 like this. So these diagonal elements I'm getting 0. So all the elements, 0 is not a member in Z. 0 is not a member in Z. So it is not closed. It is not a closed. It is not a semi-group. It is not a monoid. It is not a group. It is not a group. So additive modulo 6 is not a group. Now we are going to verify the second concept is multiplication modulo 6. Multiplication modulo 6, same thing we are going to write. So suppose I am just pick two elements, 2 and 6, 2 and 5. It is 2 and 5, it is nothing but 10. 10 I am going to write it as 6 into 1 plus 4. 6 into 1 plus 4. And the next 12. 12 I can write it as 6 into 2. So the reminders I am going to write here. Whatever the reminders that I am going to get, while this is going to be divided, and then the reminders I am going to write. So here these two I am going to add, and then if it is exceeds, then I am going to subtract, and whatever the values that we are going to get, those things we are going to write here. And here just we are going to divide, and the reminders we are going to write. So here let us consider the elements, some other elements. Let us take, I am just taking 4 or 2, 5 I am taking. 2, 5 are the elements in Z. So what is 2 multiplicative modulo 5 is? 2 multiplicative modulo 5 is, so 5. So it is a 10. So 10 modulo 6. So if I am going to get it is 4. So 2, 5, 2, 5, 2, 5, it is 4. Suppose if I am taking 5, 3, so it is 15. So 15 divided by 6. So what I am going to get the remainder? So this can be written as 6 into 2, 12 plus 3. So the remainder is 3. So 5 3s, it is nothing but 3. It is nothing but 3. So like that, if I am going to consider any two numbers, so I am just taking 3, 3 belongs to G. What is this? 3 into 3. It is nothing but 9. So 9 multiplicative 6 is, what is the remainder is 6 into 1 plus 3. So what I am going to get? 3 I have to write. So what about 3 into 3? 3 into 3 is 6. 3. 3 into 3 is 3. And similarly like that, any two elements if I am considering 5, 4, 5 into 4, 5, 4 belongs to G I am taking. 5 into 4, what I am going to get? It is 20. 20 can be written as 6 into 3, 18 plus 2. It is 20. So or else divide, whatever the remainder will be there, then that you are going to consider. So 5 into 4, I am going to get 2. I am going to get 2. Similarly 4 into 5 also I am getting same. 4 into 5 also I am getting same, like this. So this is the multiplicative modulo 6. So in this principle, by using this principle, and I am going to fill all the table by using that law, by using that rule. Whenever, if I am going to use that rule, and next whatever the resulting values that we are going to obtained in the table, we have to verify whether all the elements are members in G or not. If all the members are G, then automatically it is closed. So here once again I am getting 0. I am getting 0. 0 is not a member. 0 is not a member. So it is not closed. It is not closed under multiplicative, additive multiplication of 6. So, multiplicative modulo, this is addition and multiplication modulo 6. Addition, multiplication modulo 6 is not a group, even though it is not a semi-group also. So we can say in this way, both are not groups. So whatever the things that we are discussed here, whatever the two problems. So now let us go for the another one. So another one is, let G is given as like this. We are going to collect the ordered pairs. And the real numbers and A is not equal to 0. A is not equal to 0. Then the relation between the ordered pairs, are like this. AC, A into C, then another one is BC plus D. BC plus D. So, if I am going to consider any two ordered pairs from the group from Z, between them the relation is this. Now we have to prove whether it is a group or not. So here A, B elements are nothing but a real number system. So here we are just considering, now we have to verify whether it is a group or not. So first one is, we have to verify the closure property. Take two ordered pairs. If A is not equal to 0, it is mentioned. So, and AC is not equal to C is also not equal to 0. Because what is the meaning of this? Any ordered pair, if I am going to consider, the first element of the ordered pair is not equal to 0. The meaning of that is that, if ordered pair A comma B, if I am considering, A is not equal to 0. If I am considering the ordered pair C comma D, C is not equal to 0. If I am considering ordered pair E comma F, E is not equal to 0. The first element of the ordered pair is not equal to 0. So here I am taking two ordered pairs. Obviously A is not equal to 0, C is not equal to 0, so AC is not equal to 0. The product of these two are not equal to 0. So once I am going to apply the binary operations on this. So once if you are going to apply the binary operation, so I am going to get this. So here AC is not equal to 0. The first element is not equal to 0. Of course, the remaining are also real numbers. Because B is a real number, C is a real number, BC is a real number. Then plus D, addition of two real numbers. Again I am getting a real number. So definitely the whole thing belongs to G. Why I am considering? Because the first element is not equal to 0. So I can say that it is a member in G. So the binary operation star is closed. Now we have to verify. The associative law. So for that we have to take three elements. A, B, C, D, E, F. So here A is not equal to 0, and next C is not equal to 0, and next E is not equal to 0. So subsequently A into C into E is also not equal to 0. Now I am just applying associativeness. So first these two I am applying the definition. So I am going to get this. So I am going to get this for the first two ordered pairs, and another one is this. So first element into this one. So AC into E. Next another one is BC plus D. See here what it is given? BC, and next plus D. BC plus D. What is that? B is where it is B. So the second ordered element is nothing but this one is this into this plus F. So BC plus D into E plus F. So I am just multiplying now these two. Subsequently I am going to get this. So here ACE is not equal to 0. So I can say that this is a member in G. And now the another concept, the next one, we are going to verify this. So this is the another way. Then the right hand side, that we are going to verify. So these two ordered pairs I am going to apply, then it will become like this. So here also ACE, all are not equal to 0. So ACE is not equal to 0. So once again I am applying the binary operations of this. So A into CE, ACE, and next B, and next B, and next CE plus DE plus F. So the second one is B. So first is no problem, ACE. The second one is B, CE, and next plus DE plus F, DE plus F. So this is the ordered pair. So ACE and next BCE plus DE plus F. So this is the value that the ordered pair that I am going to get, and which is equal to the previous one, So we can say that the left hand side is equal to the right hand side. So it is associative. Now we have to verify what is the identity element. Identity element is nothing but here an ordered pair. It is nothing but G is a collection of ordered pairs. So we have to get the identity value as an ordered pair. Suppose if I am taking A, B is an element in G, and the identity element X, Y is a member in Z. I am just assuming that. So this is the identity element. Now what is that X and what is that Y? I have to find out. If I am going to assume this is a identity element, then A, B star X, Y. So this can be written as AX. Of course, this is what I am going to get. An element multiplied with binary operation with the identity element. I am going to get the element itself. Now just I am going to apply. This is AX, A into X, and next another one is B into X. So what about that? For second one is I am just taking B into X. What is that? See here it is given BC plus D. So what we are going to get? BC means BX plus Y. What is the relation? AB star CD, and it is given as AC. Next BC plus D. It is defined. So here it is defined as like this: AC, BC plus D. So C is replaced with X and D is replaced with Y. So C is replaced with X and next D is replaced with Y. So I am going to get like this. So this is equals to A, B. When we say that two ordered pairs are equivalent, whenever, see I am just taking A, B is one ordered pair and C, D is another ordered pair. When they are equivalent to each other, whenever A is equals to C and B is equals to D, then we can say that those ordered pairs are equivalent to each other. So in the same way here the ordered pairs are equivalent, then we have to say that AX must be equal to A and next BX plus Y must be equal to B. BX plus Y must be equal to B. My intention is I have to calculate what is X and what is Y. Then this I am going to write it as A into 1 by using left cancellation law. So I am going to get X is equal to 1. Once if I am going to get X is equal to 1, I substituted here B into 1 plus Y is equal to B. So I am going to get Y is equal to 0. B minus B. So what I am going to get X, Y ordered pairs as 1, 0. Observe this. 1, 0 acts as an identity element. Here we have to verify whether it is belonging to G or not. So what is the definition? Whatever the thing is given, whatever the condition will be given, that shows that the first element of the ordered pair should not be equal to 0. And the second element may be equal to 0. So here the first element is not equal to 0. So definitely this is a member in G. So we can say that 1, 0 is an identity element. Now we have to verify. That means here G is having the identity element and the identity element value is 1, 0. Now we are going to find out what is the inverse an ordered pair. What is the inverse of an element G? G element means an ordered pair. So let us consider A comma B is an element in G. Now its inverse I am just taking, let us consider it as C comma D. I am just taking C comma D is the inverse. Then if I am going to multiply, if I am going to apply the binary operation, then we have to get the identity element as 1 comma 0. Now we have to verify what is the C value, what is D value, what is C value, what is D, because we are assuming that this is the inverse of this. So A inverse should be identity element, but here identity element is 1 comma 0. Now what is this? AC, next BC plus D is equals to 1 comma 0. 1 comma 0. Now AC is equal to 1. Now BC plus D is equal to 0. Now I am going to calculate what is C. C is equal to 1 by A. And now what is D? D I have to calculate. What is D? So what is C? I substituted here. B by A plus D equal to 0. So what is D equal to? Minus B by A. So I am going to say that what is the inverse of AB is equal to CD, and C is 1 by A and D is minus B by A. Minus B by A. So now this is the inverse of A comma B. This is the inverse of A comma B, and of course it is a member in G because the first element is not equals to 0. So I can say that it is a member in G. Member in Z. So A comma B inverse is this, and this is a member in G. So for each and every element will have a inverse. So I can say that G is a group. I can say that G is a group. Now we have to verify whether it is a abelian group or not. Abelian group or not. So for that I am just taking two ordered pairs AB and CD, and then I am going to take it as the binary operation star. So it is nothing but AC. It is given in the problem itself. And now I am just taking A star B is equals to B star A, whether that is true or not. So for that I am going to take this one. So I am going to get another one is this. So now just we have to verify whether these two are equal or not. Whether these two are equal or not. If these two are equal, whenever AC is equal to CA, then only they are equal. First element equal to 0 and second element equal to same. Whenever both are equal, then what I am going to say that if this is equal and this is equal, and BC plus D and DA plus B are not equal. And so from this is not equal to this because A is not equivalent to C and B is not equivalent to D. A is not equivalent to C and B is not equivalent to D. So entirely two different ordered elements. So these two are not equal to each other. So the composition is not commutative. So it is not an abelian group. It is not an abelian group. So in this way we have to verify. So whatever the given in the example, so whatever the binary operation defined like this, and by using this we have to verify under this composition, we have to verify whether it is a group or abelian group. That we have to verify in this order. Now let us go for the other example. Let us say then the circle is a binary operation defined on Z. So what is the operation is X circle Y. If I am taking X comma Y are any two elements in Z, then X circle Y defined as like this. Instead of a star, we are taking it as here as a circle. Circle is the binary operation. Now we have to prove that Z comma circle is an abelian group. Okay. Z is an integer set. Now let us go for this. X comma Y belongs to integer. Then addition of two integers is again an integer. If I am going to add 1 is an also integer. So this is nothing but addition of integers. So it is also a member in Z. So we can say that this is X circle Y, which is also belongs to Z. Because X circle Y can be represented as X plus Y plus 1. X is an integer, Y is an integer, 1 is an integer. So addition of integers is again integer. So which is belongs to Z. So we can say that X circle Y belongs to Z. So it is closed under the binary operation circle. Now associativeness we are going to verify. So for verifying the associativeness, we have to verify X, Y circle Z is equals to X circle Y and the next circle Z. We have to verify whether this is true or not. So for that I am just taking this, and Y circle Z is equals to Y plus Z plus 1. Then X circle X plus Y plus Z plus 1 plus 1. So I am just taking X plus Y plus 1. So I am going to get like this. So I am going to rewrite this X plus Y. I am just associativeness because the addition of the integers satisfies the associativeness. So I am just taking numbers, these are the numbers, and next integer. So in any order I can take the positive values. If it is a negative will be there, then that will be different. So I am taking in this order, and which is nothing but this, So this shows that this binary operation circle is an associative. Now we have to find out what is the identity element. What is the identity element? Let us assume that, and X is the identity element if I am taking, or A is the identity element of X. Then I am just taking X circle A. I am going to calculate what is A. What is A? I just assume that A is the identity element. A is the identity element. If A is the identity element, X is any element, then the resulting is X. Or A circle X is equal to X. Anyway we can consider. Then this is nothing but A plus X plus 1 is equal to X. So now X get cancelled. So A equals to minus 1. And here if you take this also, both has to be satisfied. Then this is X plus A plus 1 is equal to X. So X get cancelled. So A is equal to minus 1. So the identity element is equals to minus 1. The identity element is equals to minus 1. Minus 1 is a member in Z or not? So minus 1 is also an integer. So it is a member in Z. Which is a member in Z. So that I can say that the identity element is also exist. Identity element is also exist. Now we have to verify the inverse. We have to verify the inverse. So now let us consider I am taking the element A. I am just taking the element of, let us consider X is the element. X is the element. X belongs to and Z. So let us assume that Y is the inverse of X. Y is the inverse of X, which is also member in Z. So now what I am going to take, X circle Y is equals to the identity element. The identity element. What is the identity element is minus 1 is the identity element. What is X circle Y? How it is going to be defined? X plus Y. How it is going to be defined? X plus Y plus 1 is equal to minus 1. So what is X plus Y is equals to minus 2. What is Y is? Minus 2 plus X. What is Y is? Y is the inverse of X. What is that? Inverse is minus of X plus 2. X is an integer, plus 2 an integer. So addition of two integers is again integer. Keeping minus 1 is also again integer. So minus of X plus 2 is also a member in Z. Is also a member in Z. And moreover, this is the inverse of X. This is the inverse of X. So we can say that Z comma circle is a group. Now we are going to verify the Abelian condition. So now to verify the abelian, x circle y is equals to y circle x. So x circle y is x plus y plus 1. Then this I am going to write it as all are integers. So y plus x plus 1. I am just changing. These are the two integer numbers. Addition, it is nothing but satisfying the commutative law x plus y is equal to y plus x. So I am going to write y plus x. Then plus 1. So it is nothing but y circle x. So this is satisfies commutative law. Already it is a group and it is satisfies commutative law. So we can say that it is an abelian group. It is an abelian group. So in this way, we are going to prove the problems which are comes under the groups. In the next class, we are going to discuss some more concepts related to groups. That is nothing but some more example. Okay, let us consider some more examples on groups and abelian groups which are satisfied on this. With this, I am going to conclude this today's session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.